Hey guys, and welcome to our next set of video notes. Today we're going to be continuing with our discussion of atoms and the periodic table, but we're going to be specifically looking at electrons and what they're doing as they're kind of floating around outside of the nucleus, and talking a little bit about certain properties that some groups of atoms share. So with that, let's get into the notes. So today we're going to be going over electron shells and reactivity. So what are electrons doing as they're floating around the outside of the atom, and how do atoms react with one another? What level do atoms react with one another at? So just for a quick review, you might remember that our atoms that we're talking about have what's called a neutral charge. So they're protons that are positive and they're electrons that are negative. So the protons are positive, the electrons are negative, and they have to be equal to each other. They have to kind of balance each other out to have a zero charge. So however many protons we have in the nucleus, we have to have that many electrons floating around on the outside. So like hydrogen, for example, here has one proton in the nucleus, so it has to have one electron floating around the outside. However, electrons do not just float randomly. They don't just kind of wander and drift and do things on their own. So they are not random. Instead, they group together in certain kind of rings, or what we call shells or orbitals. So instead of just being randomly floating around, instead they get grouped into rings, kind of like the rings around Saturn. So electrons orbit in these rings, or what are called electron shells. And there are rules about how many electrons can fit on each shell. So the first shell, the first electron shell, can only fit 2 electrons. So the very first 2 atoms in the periodic table are hydrogen and helium. Hydrogen has 1 proton and 1 electron. Helium has 2 protons and 2 electrons. And so helium has a completely full first shell, because again, we can only fit 2 electrons on each shell. The second shell and the third shell can fit a lot more. They can fit 8 electrons each. So like lithium, for example, down here has 3 electrons. And so we have 1, 2 on that first shell, but then that shell is now all full. So our third electron has to go on shell number 2 out here. So we have 1, 2 shells. First shell can fit 2, second shell can fit up to 8. Obviously, lithium doesn't have 8 or 10 electrons to go around. It only has 3. So the third electron gets to go all by himself on the outer shell out here. So same thing with carbon. We already know from the last examples that we looked at that carbon has 6 protons and 6 electrons. And so we have 1, 2 electrons. Now our first shell is completely full because we've got the 2 electrons on there. And so our next electrons, numbers 3, 4, 5, and 6, they have to go on that second shell. So 2 electrons on the first. Carbon has 6 electrons total, so there's 4 left over. Those go on the second. All right, so what about somebody like sodium? down here. We've talked about our first shell and our second shell. So sodium has 11 electrons, which means that, okay, we've got 1, 2 electrons on our first shell. Now our first shell is completely full. Then we have to put electron number 3 on the second shell, electron number 4, and 5, and 6, and 7, and 8, and 9, and electron 10 goes on the second shell. But now we have 2 on the first shell and 8 on the second shell, 10 electrons total, but now that second shell is completely full because only 8 electrons can fit. So electron number 11, we have to go out to shell number 3. So that's how we start putting electrons on the third shell. If they have over 10 electrons, then we have to start putting electrons on that outer third shell. So if we jump way over here to our argon atom, argon has 18 electrons, 18 protons and 18 electrons. So if we do those same steps again, this time I'm just going to make little marks on each electron. So we have 1, 2, first shell is full, 3, 4, 5, 6, 7, 8, 9, 10. That's 10 from 2 on the first shell and 8 on the second shell. So now our second shell is completely full. 11, 12, 13, 14, 15, 16, 17, 18. So now argon has 10 on the first 2 shells and then 8 more on the third shell, means 18 electrons total and 8 on that outer third shell. So 2 on the first shell, 8 on the second shell, and 8 on the third shell. That's how many can fit, not necessarily how many are going to be there. So let's look at some more examples. So nitrogen has an atomic number of 7, so it has 7 electrons. So we start counting. 1, 2, but now shell number 1 is full. 3, 4, 5, 6, 7. So that's 2 on the first shell, 5 on the second shell gives us 7 electrons total, but now we're out of electrons, and so nitrogen has 2 electrons on the first shell and 5 on the second shell. Neon has 10 electrons. So we have 2 on that first shell, and then 3, 4, 5, 6, 7, 8, 9, and 10. So neon has 2 on the first shell and a full set of 8 on the second shell. So 10 electrons total means that neon has both shells completely full of electrons. So over here, nitrogen with 7 electrons on the first shell, we're gonna fill it up with 2. And then the second shell, we're gonna put the 5 that get left over. And 2 plus 5 is 7. Neon on the first shell, we get 2 again. And then on the second shell, we completely fill it up with 8 electrons, and 2 plus 8 is 10 total electrons. What about aluminum? Aluminum has 13 electrons. So we start counting. 1, 2 electrons on the first shell. And now the first shell is totally full. But we're not out of electrons yet, so let's keep going. So 2 on the first shell, 3, 4, 5, 6, 7, 8, 9, 10 electrons on the second shell. But now our second shell is completely full, but we still have some electrons to go. So 11, 12, and 13 are out here on our final third shell. So there's 3 on our third shell, and 2, and 10, and 3 all together give us 13 electrons. Oh, I'm sorry. This is totally wrong. Hopefully somebody noticed that and was like, Mr. Stanley, what are you doing? There's 8 electrons on the second shell. There's 10 electrons total between shells 1 and shells 2. But as we mentioned earlier, shell 2 can only fill up with 8 electrons. That is my bad. So with 13 electrons, we have to put 2 on the first shell, 2 on this first shell, 8 on the second shell, and the remaining 3 on our third shell. So that's how the electron shells work. You figure out how many electrons are in your atom, and then you just start adding them to the shell, moving up to the next shell if you fill up the shell that you're currently on. So one of the reasons why these electron shells are very important, and it's good to know how many atoms are on each shell, or how many electrons are on each shell, is because atoms really want their electron shells to be full. Atoms, obviously, they're tiny particles and they can't feel happy or sad. But I like to think of it as atoms really want there to be a full set of electrons around their shell. They really want to have, if they just have the first shell, they just want 2 in that outer shell. If they have a second or a third shell, they want 8 to be there. And so this means that they're more likely to react with other atoms and form bonds with these other atoms if that means that they will help the electrons that they share will help their shells be full. So for example, we mentioned earlier that hydrogen has 1 proton and 1 electron in each hydrogen atom. But like we mentioned, the first shell can fit 2 electrons. So in order for hydrogen to get 2 electrons in that first shell, normally hydrogen atoms will share their electrons with each other so that they can have that full first shell. And so by this hydrogen sharing his 1 electron and this hydrogen sharing his 1 electron, they can have this full set of 2 electrons shared between each of the hydrogen atoms. For another example, let's look at sodium and chlorine. So sodium and chlorine react together very well because sodium only has 1 electron on its outer shell. So its outer shell is almost empty. It's not happy about that. Chlorine has 7 electrons on its outer shell. So chlorine has an atomic number of 17, and sodium has an atomic number of 11. So sodium only has 1 electron on its outer shell, and chlorine has 7 electrons, but it's only missing 1 electron from its outer shell. So this makes sodium and chlorine very likely to react with other atoms so that they can either get rid of that atom by sharing it with the other atom so that now sodium feels like it has a full second shell, and chlorine will accept that electron from sodium so it can feel like it has a full outer third shell. So they stick together because sodium is just kind of sharing that one electron with chlorine, but now they are much happier atoms because they have those full outer shells by sharing that one electron, so that sodium gets rid of it and chlorine accepts it. So we call this likelihood to react with other atoms reactivity. So you may remember when we talked about chemical properties of substances that how reactive that they are is one of their chemical properties, how easily and speedily they react with other elements or compounds. So, like I mentioned before, atoms are really happy when their electron shells are full. Atoms are very unhappy when they have very empty or almost full outer shells. So when this happens, by very unhappy, what I really mean is that they are more reactive because they really, really want to do a chemical reaction with another element so that they can get that full shell. They can either give away or take a new electron. So sodium is very, very reactive because it has only that one outer electron, so it is a very empty outer shell. And chlorine is very reactive because it has a very full outer shell. So if their shells are almost empty, they've only got 1 or 2 electrons on there. Or if they're almost full, they have 6 or 7 electrons on there. That makes them more reactive. The fuller that their electron shells get, the less reactive that they become. So groups and families of elements have similar reactivity. So groups and families are the columns on the periodic table. So a group or a family is what goes up and down. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 groups in the periodic table. Group 1 over here is a group of atoms that only has 1 electron on their outer shells. So like sodium that we talked about earlier, lithium we also mentioned a little while ago as only having 1 electron on their outer shell. And that's true for all of the elements of these groups. So they are very reactive. They will react very violently with a lot of other elements. Another group that is very reactive is group number 17, right here. So group 17, like that has chlorine in it, is only missing 1 electron from their outer shell. So that's what makes them very reactive, is that these guys over here, group 1, only has 1 electron on its outer shell. These guys, group 17, are only missing 1 electron from their outer shell. Group 18, these guys over here, they have completely full outer shells. These guys are extremely unreactive. They barely react with any of the other elements. And that's because they're essentially like fat and happy. They have all the electrons in their outer shells, so they don't really care about reacting with any of the other elements. They're just going to stay full of electrons and not do any reactions with anybody else. They have all their reactions. They are all good. So if you have very few or almost full outer shells, then you're going to be extremely reactive. But when you get to group 18 over here, Your outer shell is completely full, so you are very, very non-reactive. The final thing that we're going to talk about in terms of groups of atoms on the periodic table are metals, metalloids, and nonmetals. So you may have noticed that our periodic table is divided up into colors. That's not just to make it look nice and pretty. That's because our colors denote if our atoms are metals. So we have this big group right in the middle here. That's all metals. Metalloids, this little zigzaggy purple group over here. And the nonmetals, which include hydrogen and then all of these guys over here. So metals and nonmetals have very different properties from one another in terms of some of their physical and chemical properties. And then metalloids have properties that are sort of in the middle in between metals and nonmetals. So the properties of metals are, whenever you think of metals, I want you to think about things like aluminum cans, aluminum foil, copper wires. These are all metals. So they tend to be shiny. They tend to be pretty reflective of light. They are solid at room temperature. And so like you think of a hunk of metal, that's going to be a big piece of solid metal. They tend to be malleable, meaning that you can hammer them flat. They're a little bit squishy, so you can kind of squish them down into a flat sheet like an aluminum foil. They are ductile, which means that we can make them, stretch them and twist them and make them into a wire. And so like copper, or like these wires right here, are because metals are ductile. And they are extremely conductive, meaning that they transfer heat and electricity to other objects very, very, very well. This is why your pots and pans that you use on your stove are made out of metal and not like rubber or plastic or wood. Those things are very non-conductive. So even if you put a lot of heat into them, the inside isn't going to be very hot. Metals are conductive. So as soon as one part of the metal starts to get hot, it very quickly starts to spread that heat around to the rest of the metal. Same thing with electricity. So we use a lot of copper wiring in order to pass electricity from the power station to our houses and offices and businesses. And that's because copper and other metals transfer electricity through them extremely well. That's why if you see your kid poking into a wall socket with a plastic knife, they obviously shouldn't be doing that, but they're probably not going to get hurt because plastic does not conduct electricity very well. On the other hand, if you see them take a metal fork and start jamming it in there, that could cause a big problem because that electricity will conduct through that metal fork really well and possibly give a shock to the person that's poking at the wall outlet. So they're shiny, they're solid, we can squish them down into sheets, we can bend and twist them into a wire, and they are very conductive, moving heat and electricity through them. These are the properties of our metals. Nonmetals are basically a lot of the opposite properties. So they are not shiny. They tend to look a lot more dull, kind of like rocks if you see them in their liquid or solid forms. They are very bad conductors. And so things like sulfur, oxygen, carbon, fluorine, chlorine, these do not conduct electricity very well. The electricity and heat do not pass from one side or the other very easily. For the most part, nonmetals are gases at room temperature. And so when you think of metals, you think like aluminum, tin, iron, silver, gold, all of those are solid. Nonmetals, things like oxygen, nitrogen, carbon, chlorine, neon and argon that go into those cool signs in front of restaurants. These are gases at room temperature. So they normally exist in their gas state in nature, not solids like our metals. And then the solid form of these, so like sulfur is one of the few nonmetals that is solid at room temperature, but it is very brittle, meaning that it'll break and shatter very easily if you try to smush it down into a sheet. So our metals are very malleable. We can squish them and make nice flat sheets of aluminum or tin. Nonmetals, you try and do that and they're just going to shatter and break off into 1,000 tiny pieces and lots of different pieces of powder. So a lot of the opposite properties of metals. They're not solids, they're gases for the most part. They are not shiny, they're very dull. The solids, we can't really bend or stretch them, they just sort of break and shatter. They tend to be gases at room temperatures, not solid. And they are poor conductors. You cannot get sulfur to transfer heat and electricity very well. So those are our metals and our nonmetals, kind of two different sides of our periodic table. So in between those guys, we have the metalloids. So metalloids are kind of in between, literally, the metals and the nonmetals. Not only are they between them on the periodic table, they also have some properties that are in between them as well. So for the most part, metalloids are solid at room temperature, like metals. However, they tend to be very brittle and hard, like nonmetals. They can sometimes conduct electricity, but it has to be under very specific circumstances. So we call them semiconductors because they're not full great conductors like metals, but if you get them under the right conditions, the right temperature and pressure, then they can conduct sometimes extremely well. So computer chips tend to have a lot of semiconductors in them. Silicon is a really important semiconductor that goes into computer chips. Think like the reason that the area where Facebook and Google and Twitter and stuff are located in California is known as Silicon Valley, because silicon is an important aspect of a lot of computer chips and computer processors. It's also what makes up a lot of sand and is used to make glass. So metalloids are literally in between metals and nonmetals. They have some properties of metals, like being solid and being able to conduct certain electricity at certain conditions, but they also have certain properties of nonmetals. They're very brittle and shatter easily, and if the conditions aren't right, then they are not good at conducting heat and electricity at all. So we have our more reactive metals over here. Remember we talked about group 1 is extremely reactive. And then as we get more and more electrons along that outer shell, so as we move this way, we're getting more electrons. And so the more electrons that we get on that outer shell, the lower that our reactivity becomes, because we're getting more and more full of electrons. Now, nonmetals, obviously over here, we have like halfway full shells. But then remember, as we get closer and closer to filling up our shells, then we start to get more reactive again, because our group 17 right here is extremely reactive nonmetals. So the nonmetals start off as being fairly low reactivity, with the carbon and nitrogen pretty low, but then oxygen and especially fluorine are much higher reactivity. But then, again, remember that our very lowest reactivity group among the entire periodic table is this group right here, our group 18 that has completely full outer electron shells. They do not want to react with anybody else. They're good and happy with their full shells. So carbon, we mentioned a couple times right here, is extremely important for living organisms. So you and me and all of the animals and plants in our world are mostly built out of carbon. Carbon makes up a lot of our bones, our muscles. It's what we use for energy from the food that we eat. So life on Earth is mostly based on carbon. And then those 18, that group of 18, that extremely low reactivity group on the far side of the periodic table, has its own special name called the noble gases. So they're called noble gases because scientists thought it'd be funny to think of them as like medieval noble people that didn't want to interact with all the lowly peasants all over on the other periodic table. And so since they don't react, the chemists thought it was kind of funny to think of them as like stuffy aristocrats, and so they called them the noble gases. They don't want to react with any of the other elements. And that will do it for our notes on electrons and reactivity. So for the homework for this set of notes, you guys are going to be putting together an oxygen atom and figuring out how many protons, neutrons, and electrons there are in it, but also where the electrons should go on those shells. So let's take a look at what the homework looks like real quick. There we go. So we have our element oxygen right here. He has an atomic number of 8 and an atomic weight of, well, basically we'll say 16. That's really close to 16. So for the first part of this, I want you to tell me how many protons, neutrons, and electrons that an oxygen atom would have, very similar to the homework that you did last week. But the second part of this is where everything gets put into play. So we have our kind of empty atom right here. We have our nucleus right in the middle here. So we have our nucleus right in here. And then we have our 1, 2, and 3 electron shells or rings on the outside. And so your job is going to be to put all of the protons, neutrons, and electrons where they belong. So however many protons and neutrons that you figured out oxygen should have, you'll draw that many down in the nucleus down here. Now it's up to you how you want to display them. You could do P's and N's. You could do pluses and zeros for their charges. You could do shapes to determine which one is which. I don't really care, as long as you have the correct number, total number of protons and neutrons in the nucleus. And then the electrons, remember, you have to figure out where all of your electrons are going to go. So like I mentioned, we have our first ring, our second ring, and our third ring of electrons. And so based on the number of electrons that you determine oxygen has, you should put the correct number of electrons on the correct ring where they should go. So up to 2 electrons on the first ring, up to 8 electrons on the second ring, and then if you still need some more, up to 8 electrons on the third ring. All right, so number of protons, neutrons, and electrons, and then a representation of how many neutrons, protons, and electrons there are in our overall atom of oxygen down here. So that's all that I have for you guys today. As always, please reach out to me if you have any questions. You can come to my Zoom office hours, or you can shoot me a text or an email, or send a question on the Google Classroom. I'll do my best to answer it as soon as I get it. You can also, once you're finished with your homework, you can upload it to the Google Classroom or take a picture of your drawing and send it to me through a text or an email. That's all that I have for you guys today. Again, please reach out and let me know if you have any questions, but I will see you back here for our next set of notes next time.